Hi everyone, can you hear me okay? Yeah, good. Right, so yeah, I'm Matt Bellamy. I work at ARM on our automotive GPU technology. I, as a sideline, also chair the Vulkan SC working group. So I'm going to talk a bit today about Vulkan SC. So it's going to be kind of an introduction to Vulkan SC. What is it? Why is it? Look at some of the use cases we expect it to be used for. Delve into a couple of those. Talk a little bit about porting between Vulkan and Vulkan SC. Discuss actually getting hold of Vulkan SC implementations and we can do that. And after that, we'll look at some of the developer tools we've been working on for the last year or two. But first up, I've kind of thought post-lunch, as exciting as safety critical is, we'd kind of try and wake the room up. So I've put a couple of images on these slides. And I want to see if someone can connect this bottom right image to something I've just said during this talk. For context, that seat is in that plane at the top.
Seat. It's a safety ticket.
Yeah. Do you know what the plane is?
Oh, as opposed to a Victor.
Yes. So a V bomber. So that is a Vulkan bomber, and that is a safety critical chair in that plane. So it's a Vulkan safety critical chair. Slightly different to me. Right. So moving on, what is Vulkan safety critical? So like Vulkan, it's a graphics compute API. The main difference is where it's designed to be deployed. So we're designing it to deploy in devices where if something goes wrong, it's not like inconvenient, oh no, I've lost my point in the game, I've got to restart, or I'm going to kill my app or whatever. It's where if it fails, it glitches, you get the wrong results, it crashes. Someone might get hurt. Someone might die. Something very expensive might happen. And so we've taken Vulkan and redesigned bits to make it applicable to that. So these devices are normally called safety certified. So this normally means if you're designing some electronic system where if it goes wrong, someone might get hurt, you have various safety standards you comply with, which cover things like the development process you use, ways to analyze the system, identify failures and the impact of those failures, and therefore what analysis and mechanisms and protections you need to put into that device to make sure it's safe and it can't hurt or injure anyone. So what we've done is taken Vulkan 1.2, we've redeveloped bits of it so which you can implement that and put it through a device certification for those safety devices. So this has meant kind of quite a few changes. They are focused on making it kind of more deterministic, more robust, more reliable. But we still tried to keep the ability to do everything you can do in Vulkan SC. So we still have compute shaders, we still have almost all the functionality in there. We've just made some changes around it. So a sample of some of the changes we made. One of the big ones is pipelines. We've basically got rid of all the on-device compiler, shader compilers, pipeline compilers, gone. So instead, we use the normal Vulkan interface to upload pre-compiled pipeline caches, and at runtime, the implementation loads pipelines out of the pipeline cache. The couple of big drivers for this, one is compilers are very big, very complex, very error prone, and trying to develop one of those, put it through a device certification is extremely painful and extremely costly. So if you can get rid of that, you've just significantly saved the development costs. And as well as that, because of the certification process has a lot of verification and testing, you have to do like line coverage by the branch coverage, all sorts of things, and you need to do that on the final code. And if you have a runtime compiler which is generating your compile code on the device at runtime, it's quite hard to verify that code. If you move it offline, so we have an offline compiler and you generate it on your host development PC, that allows you to have a fixed binary. You can test that, load it to the device, and confirm you're running that code, and it's the code you've tested and verified. Another area of concern is memory. So when you're developing your application, it might have to run for hours or days or months. And so it has to be very robust. If there's any possible failure points in it, you have to identify them and come up with a fix for them. And one of the common issues is dynamic memory. If you use dynamic memory, your allocation can fail. And the allocation, you can call malloc and just randomly it can fail. And you can imagine if you're in an airliner and you're coming down to approach and you go malloc and it says, no, thank you. It's not a very good situation. And so one of the big changes we did was to make it so you can implement Vulkanised without dynamic memory. So to do this, what we've done is the application has to specify various object counts, command buffer sizes, command buffer pools, information to the implementation at device creation time. And this means when you initialize the device, the driver can pre-allocate all the memory it needs, and at runtime it can just change them out. And providing the application complies with the numbers it said, you won't get an out of memory. And so you can be confident it'll run. And if you don't have enough memory, the plane will, when you're at the gate and powering the plane up, it will go error, not when it's, coming into approach or taking off. So as well as kind of removing and changing functionality, we did add a little bit. So again, things do go wrong, always do, and you have to handle it. So we added in a fault reporting API. So this is a framework where if the implementation detects something's gone wrong, it can send a message to the application and say, something's gone wrong, do something. And that allows, reporting of faults of various things, correction, and the application to kind of take corrective behavior if it can and fix the issue. We also have, an optional extension we call object refresh. So if you're running this on a GPU and an embed sort of one with its own integrated memory, that memory might not have like ECC and error correction and things like that. So to avoid data getting corrupted every so often, you want to rewrite your memory. This extension allows you to have the implementation automatically kind of recopy data on a set frequency to make sure there's no bit faults in your memory. So, lots of little tweaks, but fundamentally the API remains and looks very much like Vulkan. So why did we even bother with Vulkan SC? There was this thing called OpenGL SC, proven known technology, widely deployed, been around quite a while. Well, we wanted we have all these modern GPUs, they have all these capabilities. We want an API you can expose them. OpenGL SC is stuck at OpenGL ES 2.0, and so it's very limited in its capabilities, very basic. You don't have control over copy, will the driver copy or not copy data, things like that. No multi-threading, you're very restricted shader language with ESSL 2.0. You've got no support for compute or AI workloads. So, all that was really missing. And in safety critical, we wanted a modern, fully capable API to deploy into the market. And it just made sense to base it off Vulkan. The other point is, OpenGL SC is kind of in maintenance mode. It's there. There's no updates coming, no new releases. So you can see from the table, it's not been updated since 2019. Vulkan SC, we're doing 3 to 4 spec releases a year, and it's doing that, and there will be future versions. So it has, it's a lot more future proof. So basically, if you write an application into this market, you should be targeting Vulkan SC as the future, unless you've got a sort of existing code base targeted at OpenGL, SC or ES, then it may make sense to stick on that. But apart from that, Vulkan SC is the future. So what might people use this for? Or what will people, and what are people using it for? So a lot of the use cases are automotive. So your ADAS, your self-drive, your displays, your controls, all that kind of stuff where you have safety critical information or processing data, which is critical to the safety of the vehicle. Might be robots, and they have similar constraints, data to process, things to visualize, and even into avionics. So, running the displays in the cockpit. But I think this image comes from one of the suppliers, and they've got a system where they're using computer vision to do docking of fighter planes for refueling. And that's running through Vulkan SC. So, more broadly than that, the main focus really are human-machine interfaces. So if you've got, some kind of machine, car, plane, milling machine, and it's got an interface and its operation is safety related, you've got the panic stop button or something on it, then that might be relevant. So these are things like telltales on the vehicles, ADAS, autonomous driving systems, all that kind of things you'd expect. Compute is an increasing focus. All the ADAS systems, autonomous driving is using huge amounts of GPU compute. And that's another area where, obviously, if the self-driving car goes wrong, someone might get injured. And so that's another safety critical use. And there are some where you might not be doing safety certification. So maybe you've got some, ATM or industrial panel, and you've got a touchscreen control on it, and you don't need to safety certify it. No one's really going to get injured if it goes wrong. But the kind of reliability, robustness, memory footprint fixedness of Vulkan SC could make it quite an attractive API to use there. Where it's not targeted specifically is in places where you write an application once and you deploy it to thousands of different devices or tens of devices. As you've seen, some of the pipeline cache things and stuff like that, and the object counts and the memory size, it means the application becomes much more tied to the target hardware. And so that model of write it once, deploy it everywhere, doesn't really work for Vulkan SC. We're also not particularly targeting gaming as a use case, mostly because of that portability issue. So it doesn't make a lot of sense to develop a game if you can only apply it to a couple of devices, unless you're a big, console vendor or something like that, and you've got one fixed platform you want to deploy to, then maybe you could do that. So if we jump into a couple of use cases in more detail, so this one, autonomous driving, you've probably seen modern cars, the amount of data and processing flying around in those is big. And some of that, if you're doing, driver assist or autonomous driving, is safety critical. If those things go wrong, there's a high chance of someone getting injured or significant amounts of damage. And so these have, all this safety critical compute processing and displaying of data, which needs to be done. So in particular, if we take the example of an autonomous driving car, so you've got a system which is driving the car, and then because, people don't trust computers, you want a display which shows what the driving software is doing, so the passengers can see the driving car, it spotted the car in front, it spotted this, it's behaving, it's going the right direction. So you have a screen. Now that driving the car is safety critical. So if you get it wrong, you'll drive into something and possibly hurt someone. That screen which shows you what the system is doing is not safety critical. If that screen goes blank or freezes, the car's not just going to drive into something. So it's not safety critical. It's what we call a mixed criticality system, where bits of it are safety critical, bits are not. And so if you look at how that's currently done, at the minute, it's done by splitting them out. Because of the way safety standards they say if you have safety workload and a non-safety workload, you have to be able to prove that non-safe workload cannot in any way impact the correct operation of the safe workload. And so generally what will happen is you will split it out and partition it away. In this case, we're using virtualization. So we have two VMs here. We have a VM which contains all the self-driving software, which is driving the car. And we have a VM which is rendering that output. Now, we have to do that because we're rendering that output using Vulkan or OpenGLAS or something like that, a non-safe API. So we can't certify that software. And because we can't certify it, we can't prove which it can't impact the self-driving software. So we can't have that driver stack running in the safety critical workload VM, because proving something as complex as a Vulkan stack running an OS and proving that can't break anything else is very difficult. So we move it out into a different VM, but then we have the problem, well, that application to render needs lots of data, which is in the safety critical domain. So now we've got to route huge amounts of data between these two VMs to run that display and update it while ensuring the safety critical VM running the driving software cannot crash. Now, if we change that to Vulkan SC, well, what you can do now is you've got a certified graphics stack, which will not crash the VM. So you can simply drop that in that VM and you can put your rendering application in that VM and combine them all. And because the certified stack's been correctly developed, all the ways it fails being identified, corrected, done like that, you can just have a single VM and have that rendering the display and driving the car and have confidence which the rendering of the display is not going to crash the self-driving software. If we move on, another little more traditional one. So clusters on modern cars have getting mostly digitized and rendering, but you have a little bits of information on those screens which are considered safety critical. So those are nicknamed telltales. So those are things like brake warning lights, gear indicators, things like that. And those are considered safety critical because if your brakes fail and it doesn't put up a light which says your brakes have failed, you're not going to slow down soon enough before the corner and you may crash and injure yourself or for people. So normally those would be certified. In this case, it's automotive, so it'd be ISO 26262. Traditionally, how this is handled is because you want some fancy graphics for the non-safety critical content on that screen, you have a standard graphics application, not safety developed, just rendering the various needles and dials because those aren't particularly safety dependent. You don't if the speed on your car fails and doesn't tell you how fast you're going, well, you can look out the window and know approximately how fast you're going. So that's not classed as a safety relevant bit of information. So what happens is you have that QM application, we call it, rendering all the fancy dials and things, and then you have a separate subsystem which is in charge of those telltales. And that is a safety certified application. Now, that might be a little software renderer running, which just draws the icons when they're needed. Or it could be a little safety setting application which checks the QM application has rendered them when needed. There's various things to do, but the point here is you end up with two applications doing things and coordinating to make sure it's safe. If you go to Vulkan SC, well, it all becomes safe. You just need one application and you can trust it just to render everything. So it can simplify your development. So we talked how similar it is. It's Vulkan. You have to deal with the offline pipeline cache and the changes there. You have to do the object counts and things like that. But basically, it's a small amount of porting work to move an application from Vulkan to Vulkan SC. NVIDIA's done a couple of things here. So they have a little triangle example, which they say is 50 lines of changes to move between Vulkan and Vulkan SC. And then they've got one of their reference confidence view applications. And they say that's around 1,000 lines code change between them. So it's not nothing, but it's not rewrite all your applications to port between them. So moving on, all sounds great. I want to play. How do I play? Well, if you want a production platform, something you can put in a car or in a plane, go to market, two options at the minute. One is a driver from a company called Core API, and they focus around drivers predominantly into avionics historically, but now also into automotive. So if you have a box and you want a safety critical driver for it, you can go to Core API and say, please can I have a driver for this box? And they'll sort that for you. NVIDIA also have drivers available for various devices, including the Jetson platform. So I think there's one of those outside, which is running some Vulkan SC, one of the neural texture demos is running on top of Vulkan SC, and I think Vulkan as well. So you can get a driver for that. But the kind of real reason I'm here talking about this, and it's not just because my desk's 100 meters that way, is because we've been making a bit of strides in availability of platforms, so we can actually now kind of enable developers to easily get platforms. So if you happen to have a recent modern NVIDIA GPU in your development system, you can just go and download NVIDIA's Vulkan SC driver from their website and the associated SDK and run it. So that's pretty easy. You can go and play. If you don't have an NVIDIA driver or you don't want to, we've been partnering with a company called Rastergrid to develop ecosystem tools. One of the more recent ones we released in December was what we call a Vulkan SC emulation layer. So this is a Vulkan SC implementation which sits on top of a Vulkan driver. So if you have a Vulkan device, which is Vulkan 1.2 and supports the Vulkan memory model, you can just download this layer, run it on top of your Vulkan thing, and you've got a Vulkan SC development environment. Along with, we've now got, the last thing we released was a little Vulkan SC cube demo. So we've got, the emulation layer and a demo which runs and uses it. So you can now just literally go on your PC, download these components, and spin up Vulkan SC and start developing applications with no hardware requirements. And then along with this, we have other deliverables, ecosystem tools. So obviously we have the specification, being a Khronos standard, headers, and we've developed a Vulkan SC loader. We don't expect that'll be used on a lot of production devices, but for development platforms, it's a useful tool. We've got Vulkan SC validation layers. So not only can you develop, you can run your application against the validation layers, check your valid usage. Various other little tools around pipeline caches. We've got Vulkan SC info tool. And then, as I mentioned, the emulation layer, cube sample. So now we're building up a fairly big suite of tools. It's, you know, it's not as big as Vulkan, obviously, but we're getting that core set of tools. And one of the next things we'll be looking at is packaging it all up into an SDK and making a kind of single SDK package available for people to use. So with that, any questions here? You've got links to the main platform providers and also, you know, our webpage and Discord link if you want to ask questions.
Hi. You're talking about reducing the number of applications so you can just use Vulkan SC. If you've got a use case where you still want to keep them separate, but you want to use Vulkan in both of them, is it possible to interop a safety version with a non-safety version? So, for instance, in your Telltale one, you want your main dashboard to still be drawn by a safety critical one, so you know it's going to keep going. But the bit that produces the lovely shiny images of the sat nav or what have you can then be run by a far more flexible system that might be downloading content and stuff from your map system, and then interoperating the two of them in an efficient manner.
Yeah, systems do that, and they generally do it using virtualization. You have like a virtual machine which is running the Vulkan SC stack for that content, and then you have one or more virtual machines just running a standard Vulkan stack. And so the APIs were not designed really for both APIs to exist within a virtual machine. Because of the isolation required for safety, we kind of expect the Vulkan and Vulkan SC to live in different virtual machines.
Okay, thank you.
Would it be fair to say that GPU info would not be a valid resource to look at as far as like all the different things that are available for Vulkan SC, since it's trying to cover everything? Or
Yeah, you won't see any Vulkan SC
gotcha.
devices there because they're not public open platforms. They're all proprietary, hidden away in work, you know, people's desks and stuff.
Thanks.
Yeah, I saw in your slide that the Vulkan SC is certificated by ISO standard.
So it is not certified. We are, as Khronos and a standard people, we're not making any certification claims about Vulkan SC. We have designed the API so which the implementers of them, people like Core API and NVIDIA, can create a implementation and put that through certification themselves. So if you want a certified Vulkan SC, you would go to someone like Core API or NVIDIA, and they would be able to supply you the driver and the certification package to go with it.
Sorry, so is Vulkan SC or ISO standard?
No.
Okay. So how about extensions? What will how will Vulkan SC support the future Vulkan extensions?
Yes, so we can pull extensions. We do support some of the standard Vulkan extensions, and kind of on demand, we can enable Vulkan extensions on Vulkan SC. And sometimes we need to tweak them a bit, for like object counts and things like that. But we can, if someone wants a particular Vulkan extension, we can normally, enable it in the Vulkan SC specification and CTS testing.
Oh, okay, thank you.
Any more questions? Yeah.
In your experience, what are the recommended VMs or containers for using Vulkan SC that you've seen?
It's really up to the implementers.
Yeah.
It's, it's all platforms seeing it OS and so it's very embedded. Yeah.
Fair enough.
We're agnostic as a standard.
I'll try to same question, but do you know like which RTOSs it's been certified on, like say VxWorks or Wind River or Green Hills? Because that's the VMs you're talking about where they do the segmentation, right? So like if you're aware of any.
I'm not publicly aware of specifics because that's all, people keep it quite secret. No one's told me, oh, we've got Vulkan SC and here's the certificate and we did it on this.
Well, I know, yeah, you guys want to have the
So,
certificate, but
they-
yeah, those
they-
would be when you're saying VMs or whatever,
Yeah.
but they do the segmentation.
You're right in the choice of OSs. We expect it to be deployed. It's more on those certified embedded OSs and stuff.
Right. Okay. Thank you.
Okay, I think that's it. Questions? Thank our speaker.